In this video, we will discuss the statistical characterization of random variables. In a previous video, we saw how can we use probability distributions to characterize a random variable. However, the probability model is not always available. In this case, we can use summary statistics to describe a random variable. Probably you have already heard about average summary statistics, such the mean, median, or mode. And other statistics are represented by the standard deviation or variance and the interquartile range, and these are used to characterize the dispersion of your experimental data. Suppose you want to know the number of goals that the PSV scores per match because you want to make a prediction on the next match. One thing that you can do is to look at the last 10 games and calculate some statistics from it. Suppose this is the result of your experimental set. So you have a different number of goals per match in the last 10 games. Another way to look at this is to tabulate the number of goals and the number of times that the PSV has scored that number of goals in the last 10 games. For example, here 0 is happened twice, in the 5th game and in the 7th game. When we calculate the statistics, we see that the average, the mean is 1.6, the median is 1.5, and the standard deviation is 1.26. To calculate the mean, we can simply sum all these values and divide by the number of matches, or we can also do a weighted average based on this table. In the previous example, we calculated the summary statistics of a random variable based on observed experimental data. Now suppose you don't have this experimental data available, but you do have the probability model underlying this data. Then you can use the expectation to calculate the average statistic. So the expected value of a random variable is calculated as the average sum of the probability mass function over the range. And for continuous random variable, the summation becomes an integral. However, it should be noted that the expected value and the mean are not synonyms. To better understand this concept, let's take again the example of the number of goals scored by the PSV, and suppose now that by looking at a very high number of games, we build a probability mass function for the number of goals scored. And we see that this probability mass function is given in a formula for goals that goes from 0 to 7. So this is the range of a random variable. Then we can use the expectation operator to calculate the mean as the weighted average of the probability mass function over this range. And we obtain that the mean is equal to 1.54. To avoid confusion between the case where the mean is calculated from a set of observations and the case where the mean is calculated from the underlying probability model, we like to use the word sample mean in the former case and expected value in the second case. However, mean is often used as a synonym for both cases. To better understand why these two words are not exactly synonyms, we can look at the formula we used to calculate the average goals scored by PSV. What we used was the weighted average. So basically we look at the number of goals and the number of times that those goals were scored and divided by the total number of games. And then if we look at the definition of probability, the frequentist definition, this is given by the limit for the number of samples that goes to infinity of the number of times a certain event occurs over the total number of trials. Now, if we substitute this probability in the formula for expectation, we get this formula. However, here the limit is not dependent on g, therefore we can take it out of the summation, and what we get is that the expected value can be seen as the limit of the sample mean for a number of trials that tends to infinity. One important property of the expectation operator is that it is linear. That means that if you have a, b constant and x, y random variables, and we want to know the expectation of a times x plus b times y, then this is given by a expectation of x and plus b expectation of y. In fact, the expectation of a deterministic constant is equal to the constant itself. The expectation is also a positive operator, and this is also a consequence of the probability axiom, because the expectation operator operates on a probability mass function or a probability density function, and therefore is if x is larger than y, then the expectation of x is also larger than the expectation of y. Finally, for a deterministic variable, the expectation of this variable is equal to the variable itself. The expected value can also be calculated over a function of a random variable. Suppose you have x random variable and y, which can be calculated from x by applying a function g. Then the expected value is simply calculated by substituting for x g of x in the formula of the expected value. Another important statistical property of a random variable is the variance. So for a random variable x with the expectation mu x, the variance is calculated simply by taking the expected value of the random variable minus its expectation squared. However, as you may notice, the variance of a random variable and the random variable itself have different unit of measures, because the variance is squared. To avoid this, sometimes the standard deviation is instead used, that is simply given by the square root of the variance. To better understand the information provided by the variance or standard deviation, we can make an example similar to the previous case. Now we look at the average goals scores by NEC in the last 10 games, and suppose that NEC scored 0 goals in 8 occasions, while scored a very high number of goals, 8 goals, in 2 other cases. In this case, the mean is 1.6. However, the same mean we obtained for the case of PSV, where we had a completely different number of goals per game. But now if we look at the standard deviation calculated for NEC is much higher than the standard deviation calculated for PSV. So only looking at the mean, we cannot say much about how NEC and PSV behave, but when we know also the standard deviation, we understand that the PSV is much more consistent and we can make a better prediction for the next game, while NEC is not very consistent. And therefore, it's difficult to make a prediction for the following game. The expected value and the variance are moments of a random variable. Moments are ways to describe the probability distribution associated to a random variable. The expectation is the first moment and describes the center of gravity, while the variance describes the spread. More in general, the mth moment of a random variable can be calculated by taking the expectation of the random variable to the power of m. The formula here can be easily obtained by using the formula given before for a function of a random variable. For example, the expectation is simply obtained when m is equal to 1. For this reason, the expectation is the first moment of a random variable. In a similar way, the central moments can be calculated by taking the expectation of the random variable minus the expected value to the power of m. And from this, you can see that the variance is the second central moment of a random variable, because if we substitute here a 2, we obtain the formula for the variance. Finally, we can calculate also normalized moments by taking the central moment and normalizing by the standard deviation to the power of m. As we mentioned before, the first moment of a random variable is the expected value and represents the center of gravity. So in this example, we have two identical probability distributions, PDFs, that differ only by their center of gravity, with the mu of x2 being larger of mu of x1. The variance is the second central moment and describes the spread of a probability distribution. For example, here we have two probability distributions with the same center of gravity, but the blue probability distribution has a larger variance of standard deviation of the red probability distribution. And this can be already known by calculating the variance without knowing the complete probability distribution. The third normalized moment of a random variable is also known as skewness and describes the degree of asymmetry. So if we have a probability distribution whose center of gravity is represented by the dashed line, when this probability distribution is exactly symmetrical with respect to the center of gravity, the skewness is zero. While in this case, for the red probability distribution, the skewness is negative, while for the blue probability distribution, the skewness is positive. The fourth normalized moment of a random variable is also known as kurtosis and provides a measure on the combined weight of the tails of the probability distribution compared to the rest of the distribution. Let's look again at the example of the number of goals scored by NEC and PSV per match, and the case where we look at the last 10 games. So we're looking at 10 observations. Suppose we want to make a prediction for the next game. If we only look at the sample mean, we don't know much about the behavior of NEC and PSV because both these teams score in average 1.6 goals. However, when we look at the standard deviation, we already see that NEC typically has a much larger difference between the goal score per game and its mean. Also, we can look at the skewness, and also the skewness is much larger for NEC as the kurtosis. And the skewness describes the difference between mean, median, and mode, while for a symmetric distribution, mean, median, and mode, they are equal. For a very skewed distribution, these three are different, and this is represented by the skewness. And the kurtosis tell us that in the case of NEC, we have an heavy tail. Therefore, by looking at all these statistics, we can expect a much larger deviation of the number of goals scored by NEC compared to the number of goals scored by PSV. Bear in mind that in this case we are using a set of observation. We are not using a probability model, so it would be more correct to talk about sample mean, sample standard deviation, sample skewness, and sample kurtosis. With this example, we conclude the screencast on the statistical characterization of random variables.